This video introduces a framework for detecting and fair payments in smart contracts. Smart contracts were introduced by Ethereum to perform transparent and traceable transactions on blockchain. We have already seen a lot of contracts for cryptocurrencies, for game, lotteries, and stuff. We also have contracts for e-voting, insurance, and supply chain as well. Those applications point to various forms of security attacks. In words, since smart contracts are often associated with real-world assets, any contract vulnerability may lead to money loss and financial disorder. For example, the DAO attack in 2013, which cost over $50 million to be stolen on Ethereum. Specifically, the attacker started the attack by sending a transaction to the DAO contract to call the withdraw function. According to the service logic, a payment will be made from DAO to the sender of the transaction, with an execution context switch as well. However, the fallback in the attacker maliciously calls back to the DAO repeatedly to receive more unexpected payment before the balance is updated and lifeline. Payment attacks like this were classified as reentrancy bugs and widely discussed in previous research. Unfortunately, heuristics adopted in existing analyzers are often imprecise in many cases. In this demo paper, we highlighted a new security abstraction for payments in Ethereum smart contracts called unfair payment. Compared to the pattern-based heuristics in the literature, unfair payment provides a way to analyze the root cause of a broken payment. Besides, we developed an analysis framework, SAFEPAY, to automatically detect unfair payment in Ethereum smart contract. We also conduct a large-scale evaluation in Ethereum and found previously unreported payment problems. The key insight behind is a new security variant called fair value exchange, which models the fairness of blockchain payments. Based on fair value exchange, and unfair payment is flagged if a violation of fair value exchange is found. Firstly, we define the value of Ethereum in two formats, Ether and token, where Ether is a cryptocurrency or Ethereum. Token is often implemented as a specific storage data. A contract value transfer can be the transfer of Ether or the transfer of token. And the fair value exchange is designed to model a transaction scenario T, which contains single or multiple transactions. We said that T is an fair value exchange if at least one of the following conditions hold. The first condition is that the amount of Ether received by a specific address R is not zero. The R needs to pay the corresponding token. The second is T only permits some specific address to execute. The figure shows an illustrative example. In a transaction scenario with 4 transactions to a smart contract Congress, the attacker enforced a specific order of transactions. The first transaction listed himself as an owner, the second added himself as a member, and the third inserted a new proposal, and the last transaction made a payment from the contract to himself. The 4 transactions were packaged into a block in the process of mining. Given different values of gas, the specific ordering can be accepted in other Ethereum pairs with larger probability. The transaction scenario broke fair value exchange by involving either transfer to proposal, but without any data value transfer, therefore lead to an unfair payment. Based on the fair value exchange, we designed a framework called SAFEPAY to automatically detect unfair payments in Ethereum smart contracts. Generally, for public interfaces are provided for users to integrate SAFEPAY with their own software. Request and response are designed to start security analysis and retrieve output. Config and require are used to specify and check financial parameters. Given an input smart contract, the input preprocessor is designed to produce necessary information for further analysis. Next, the CFG builder is called to generate the control flow graph. Security analysis in SAFEPAY started from the module symbolic execution engine, which is designed to symbolically execute possible transactions of the given smart contract CFG. During a CFG of a smart contract is being symbolically executed, a metadata generator is repeatedly invoked to produce transaction metadata for security analysis. The detection of unfair payment is performed by the core detector in SAFEPAY, which take as input a group of transactions metadata and produce a JSON report for unfair payment issues. The core detector is invoked by symbolic analysis agent at runtime. The algorithm to detect unfair payment works as follows. First, generate transaction scenarios, a set of transaction scenarios. Then analyze the transaction metadata for each transaction scenarios. After that, the core detector update the transfer of Ether and the transfer of token for each address. Then detect unfair payment in transaction scenarios according to the definition of unfair payment. The above process will be repeated until the transaction scenarios are fully covered. The preliminary evaluation for SAFEPAY were conducted on 2 open-sourced security benchmarks. Compared to existing analyzers, SAFEPAY were more accurate on the 6 cases, the first for a buggy and the last 2 are no buggy. We have also conducted a large-scale evaluation of deployed Ethereum smart contract. In terms of accuracy, over 14% reports from other analyzers were false positive, where only around 12% for SAFEPAY. There were also cases where SAFEPAY reported unfair payment problems that were missed by others. Currently, the SAFEPAY framework is implemented in Python as a command line tool for Linux-based operating systems. SAFEPAY is running a script to start a detection. As specified the input field, B is the number of transactions in transaction scenarios. Source indicate the input is a source code contract. Next, we show a user case. The input field is the source code of simple DAO. Anyone can call line 12 multiple times through the fallback function to get any amount of Ether without paying the corresponding token. Next, we use SAFEPAY to analyze it. SAFEPAY successfully detects that the payment in line 12 is fairness, and the report also gives a further explanation. The recipient is arbitrary, which means that the user could fix the bug via any restriction on the caller. Besides, SAFEPAY also provides a text case to trigger the bug, which helps to replay the transaction scenario. In the future, we plan to extend the SAFEPAY for more security problems. We also try to extend SAFEPAY to support other smart contract languages.